Alright, hello everyone. This is the exam 4 review. This is the one that Dvorka has gone ahead and posted on Canvas, so you can go ahead and find it underneath week, I think, 11 materials. But yeah, so feel free to move along. This is most likely going to be kind of long, so skip to wherever you need, but I'm going to go over the whole thing. So let's just jump right into it. So, unlike Dr. Howe, Dvorka has gone ahead and given us some true or false questions. So let's just go ahead and do those. So, unfortunately, just like you guys, Dvorka has not given me the answers to these questions. So you're just gonna have to take it with a little bit of faith and a pretty decently sized grain of salt. Um, I think I do know the answers to these questions, and I'm going to give my reasoning for why I think those are the answers, but I could be wrong about them. So please bear with me. Okay, so let's get started. So true or false? Number 1, activation energy is the energy required to initiate a reaction of breaking bonds in the reactant molecule. Okay. So, the thing about whenever we're doing a chemical reaction, what are we doing? We are changing the molecular structure of a compound or atomic, not necessarily atomic structure, but more like a molecular structure. So let me just look this up real quick. So this image is perfect actually. So let's look at this. Okay, so here we have two free energy diagrams, and of course free energy is Gibbs free energy. We can go over like the equation, what that means later. I'm not sure how important it's going to be to you guys because the Gibbs free energy equation is most likely not going to be on the exam. By the way, if you hear any meowing, that is my little boy, Link. He's quite needy, so if you'll bear with me with that too. Um, okay, so here on the left we have an exergonic reaction, and here on the right we have a endergonic reaction. So look at this. Look at what's happening here, right? In both cases, I'm sorry. In both cases we have an activation energy, right? In both cases, I mean that's what's so important, right? But in order to make something new, we have to break something down first, right? Especially in the case of exergonic, right? And exergonic, that one's easy, right? We're taking something big and we're breaking down into something small. For example, glucose into CO2, right? Or let's say fats also like fats or oils also into CO2 and water. It's just this breaking down of molecules, right? So that's what's happening here. We always have to break something down before we either leave it broken or we're going to build it back up, right? So that's what's happening here. So I would say that number 1 would have to be true. Activation energy is the energy required to initiate a reaction of breaking bonds in the reactant molecule. I'm going to say that's true. So, how about number 2? Enzymes increase free energy released from metabolic reactions. So let's go ahead. So what I just showed you was just a regular free energy diagram. But now what I'm going to show you is a free energy diagram with an enzyme. So let's see this. So what's different here? Well, actually, I'm going to see if I can find a different one. Um, just give me one moment. Okay, this one, I guess this is better. Anyway, so look at what's going on here, right? So, number 2 is asking, enzymes increase free energy released from metabolic reactions. So what is going on here, right? So look at here. the free energy is lower than what we started with. So free energy is lower than what we started with. That's negative delta G, and that is exergonic, correct? Exergonic. And we can go, like, once again, we can go over a little bit, just some review of what that means as well. Anyway, so let's see here. So we start with the substrate and we end up with the product, right? But look at here, right? If the difference between an enzyme catalyzed reaction and a non-enzyme catalyzed reaction, well, the only thing that's changing is the activation energy, because they both end up in the same spot, right? They both end up in the same, like, they both end up at the same energy level. There was no increase of energy, there was no decrease of energy. The only thing that changed was the activation energy. So the thing about enzymes, right? Enzymes will catalyze reactions that otherwise would have probably never have happened, honestly. There's some reactions in our bodies that without enzymes it would take literally millions and millions of years to proceed. So with enzymes, we're able to lower this activation energy. We are able to make things more efficient, make things more effective, and that's why enzymes are so important. However, there's no increase of energy, because the thing about enzymes as well is that it's the same chemical reaction. With or without an enzyme, it's the same chemical reaction. We're starting with the same products and we're starting with the same reactants and we're ending with the same products, right? So there is no change in energy release. So therefore, right? Therefore, number 2 will be false. Enzymes increase free energy released from metabolic reactions. That is false. Enzymes do not increase free energy. So, how enzymes change shape due to chemical reactions and chemical interactions with the substrate. That is absolutely correct. So let's see. I'm gonna look up a little. Ah, yes, here we go. This is perfect. Actually, this will be a better image. So what I have here is what's known as conformational change, right? That's what this diagram is showing. So what's going on here, right? So if you see, right? I mean, I think Dr. Howe might have mentioned this before. You'll have to bear with me if my voice sounds any funny or whatever. It is kind of early in the morning. Sorry. Anyway, so look at what's going on here. Right, there's a chemical reaction going on. We're taking this green structure and we're breaking it down into this blue, into this yellow. But look what's happening here. Focus at the active site of the enzyme. So the site in which the substrate will actually bond and will actually bind and actually do chemistry, that is the active site. All this other stuff, that we don't really care about this other stuff for now, anyway. Actually, it was, sorry, no, that's misleading. We care about the active site because this site in the middle, that's stuff that you learn about in more upper division courses. Anyway, here at the active site, that's what we care about. So look at this. So Dr. Howe was mentioning that enzymes are kind of like a beanbag, right? If you sit in a beanbag will change its shape according to how you're sitting in it, correct? I mean, like, if you think of a normal chairs do not change their shape, but beanbags do. So we could think of enzymes kind of like beanbags. So we could see as we have an enzyme entering through here, we could see that the shape of the enzyme is actually changing in accordance with the substrate. And then once the products leave and the enzyme has completed its chemistry, right? It's completed what it's got to do. Then we could see that it actually goes back to normal, right? So that's what's going on here. enzymes will change their shape due to chemical interactions with the substrate. That is absolutely true. Because, like I said, it's like a beanbag, right? With a substrate, the substrate that's going to sit down in the beanbag changes its shape, and once you leave, it goes back to normal. So that's the thing about enzymes. So real quick, let's define what a catalyst is. So a catalyst is something that a catalyst is something in chemistry that speeds up reactions. It is reusable. And there's one that I'm missing. You have to forgive me for not remembering. But anyway, these are the big two. These are the big two. So a catalyst will always speed up the reactions, right? And it will always be reusable. In this sense, we can consider enzymes to be catalysts. So it's like kind of like one of those things where all enzymes are catalysts, but not all catalysts are enzymes. For example, sometimes you will see, in fact, as a matter of fact, in some of your organic chemistry classes, if you're taking that, you'll see some metal catalysts, something like platinum on carbon or palladium on carbon. Those are not enzymes. It would be really bad if we ingested palladium on carbon or platinum on carbon. But those are in fact catalysts. But of course, not all enzymes are not all catalysts are enzymes. So that's what I'm just trying to say here. I don't know why I'm mentioning this. This is not really important. Anyway, enzymes are catalysts. So that's something to remember. And remember what the definition of a catalyst is. So it's catalyzing these reactions. It's facilitating these reactions. It's making these reactions go by quicker, easier, efficiently, that sort of thing. So we're going to go ahead and just erase this. And then, so of course, we said that number 3 is, sorry, of course we said that number 3 is true. Enzymes change shape due to chemical interactions with the substrate. So once again, I'm like only 3 questions in, 3 true or false questions in, and I am running 13 minutes currently. So I'm going to speed things up a little bit. I tend to over-explain things like I am right now. So let's move on. So number 4 is asking, enzymes easily acclimate to a range of temperatures and pHs, making them useful for many metabolic reactions. So this is one of the ones that I'm not 100% sure on. The thing about enzymes, especially in fact most proteins, so most proteins, so there's a couple things that's really important. Our bodies operate at a specific temperature, pH, and fluidity. So what does that mean? Right? It means that we don't want things to get too hot, too cold. We don't want things to get too basic or too acidic, and we don't want things to get too fluid or too stiff. There's a fine balance that our bodies will always maintain in order to keep homeostasis occurring. So, what does that mean? It means that enzymes so more specifically, this especially applies to proteins. So like I said, take this with a grain of salt because I'm not 100% sure about the answer to this question. So enzymes easily acclimate to a range of temperatures and pHs, making them useful for metabolic reactions. Well, that may or may not necessarily be true because especially proteins need to operate at a specific temperature and a specific pH. Otherwise, the protein will start to unfold. However, at the same time, there does need to be some, room for error, some room for flexibility. So it would make sense that they would be able to have a range of pH or temperature. However, it's not the fact that if enzymes were able to easily acclimate to range of temperature and pH, if they were able to do that, right, that wouldn't necessarily define their usefulness. Their usefulness is is in the fact that they could speed up reactions, of course. So for the time being, I could be wrong. So I'm going to put a star next to the ones that I could be wrong on, right? I could be wrong on this one, but I'm going to say this is false. Because like I said, proteins operate at a specific range and pH, a specific range of temperature and pH. So I'm going to say that one is false. But like I said, if it's wrong, you could come at me and you can just you, you could, in fact, you could slap me if that's wrong. Well, I'm not that confident actually. You could yeah, you just complain to me if that's wrong. Anyway, so number 5 is asking NADH passes the electrons to the electron transport chain. So once again, this I don't like this question because the language is really confusing. So I'm going to put a star next to this one too. The language is really confusing because if we look at the electron transport chain, let's look at the electron transport chain. Sorry. Let me just pull that up real quick. Okay, so this is your ETC, right? So the ETC has different complexes associated with it. So we have from 1 all the way to 4, right? And the point of the ETC is to transport protons across this membrane space, so we can create this high concentration of protons to create a chemiosmotic we can. Sorry, I'm just throwing a bunch of jargon at you. we're basically just gonna create a dam, and we're gonna use that dam to power ATP synthase later on. So let's look at the ETC, right? The ETC, we're using these electrons in NADH. We're using these electrons to go through the ETC, and eventually we have the electron acceptor, oxygen, and water at the end here. So, sorry, we have the electron acceptor, oxygen, which then turns into water. So that's what's happening with the electrons, right? So let's see the question again. NADH passes the electrons through the to the electron transport chain. I don't necessarily want to say that is true, but I could see why that would be true. So let's read it again. NADH passes the electrons to the electron transport chain. So I think if we kind of reverse engineer the question, I think what it's asking, right? And this is kind of what I don't like about these true or false questions. They seem to be very, like, you have to kind of jump around. You kind of have to like see the language that's being used. So it's really important that you pay attention to these questions, because most likely I don't know how Dvorka proctors her exams, but you will need to note the differences between her and Dr. Howe. So, well, this is one of the differences, and this is one of the differences, that being the true or false questions. But that's why I'm here to help, right? So let's look at this. So let's continue on. So let's look at this. NADH passes the electrons to the electron transport chain. So what's happening here is that the NADH isn't literally passing its electron to oxygen. That's not what's happening. And it is not passing its electron through these complexes to be accepted into oxygen. However, NADH is donating an electron. So it's donating an electron to the protein complexes, so we can power the electron transport chain. So when it says NADH passes the electrons to the electron transport chain, I think what it's asking is, where do the electrons come from in the ETC, and which they do come from NADH. So I'm actually going to change my answer. This is going to be true, I believe. But once again, if that's incorrect, you can take it up with me, because once again, I'm not 100% sure of the answers to these questions. Sorry. Okay. Anyway, so number six is asking oxidative phosphorylation accounts for most of the ATP synthesis in cellular respiration and occurs in the inner membrane of the mitochondria. So I'm gonna do a quick Google search if you don't mind. Okay, so one quick Google search later. Sorry, my cat is kind of being a bit of a nuisance currently. Um, so so obviously you won't have Google during the exam, but I am just trying to answer these questions to the best of my ability. So the reason why I look it up, right, is because I'm not because oxidative phosphorylation is kind of between the inner membrane and between the mitochondrial space. So let's so if you'll once again if you'll excuse me for one moment. So this is from Khan Academy, which we love Khan Academy, right? Oh, that's way too big. Okay, just one more second. I'll find a different image. Okay, this is from a different university. It looks like. Okay, so let's look at here. So out here, this is our inner membrane space, right? And then over here, this is our mitochondrial matrix. So you could see why you would think that it happens either in the mitochondrial matrix or within the inner membrane space. But of course, we consult Google. Google tells us that oxidative phosphorylation takes place within the inner membrane space. So we're just going to go with that. However, let's look at the rest of the question. Oxidative phosphorylation accounts for most of the ATP synthesis in cellular respiration and occurs in the inner membrane of mitochondria. So, if you remember, right, what are we making in the citric acid cycle, or the Krebs cycle, or the tricarboxylic acid cycle? You could call it anything, right? But what are we making? We're not really making ATP, are we? That's not the primary product of those reactions. So in glycolysis, right? In glycolysis, we're trying to make pyruvate, and then from pyruvate we're making acetyl CoA, and from acetyl CoA we feed into the citric acid cycle, not to make ATP, but to make NADH, right? So if you look at all these processes, you'll see that ATP synthesis is not really the primary goal. The goal is to make as much NADH as possible. So what does that mean? It means that we feed the NADH into the ETC, and then through the ETC, we make ATP. The synthesis of ATP occurs during oxidative phosphorylation, in which that happens in the in the inner membrane of the mitochondria. So this answer, this question would be true. So number seven, most of the energy harvested from glucose is eventually released as heat. That is true, because if you just think about everything, every process that you do, right? Just think about where all that energy is going, right? It's eventually going to be released as heat. If you exercise, right, you get hot, right? You're burning all that glucose, you're burning all those energy stores, and then it's going to get released as heat. So in fact, yeah, just most of the energy harvested from glucose is eventually released as heat. That is true. We just think about like the thermodynamics of everything. Um, if we break down a bunch of stuff, we break down a bunch of glucose. Eventually, some of that energy we harvested from glucose needs to be released as heat, because we can't. If it weren't released as heat, we would operate at like 100% efficiency. And if that were the case, well, then we wouldn't really need as much food. So, it's like a whole thing. Anyway, it would be eventually released as heat. So, Number 8, the citric acid cycle participated in anabolic processes. So this, right off the bat, is false. So remember, sorry, what is anabolic versus catabolic? So let's go ahead and let's do that. Anabolic versus catabolic. So in fact, let's make a little bit of a T-chart here. So both processes are part of both processes of course metabolic, right? That's metabolic. So both these processes are metabolic, but what are we doing in these processes? So anabolic, we are building up molecules. We are making molecules. In catabolic, we are breaking down. That's the difference between anabolic and catabolic. That's the main difference. And then, sorry, once you start getting into it, anabolic, we could say, are usually endergonic. Catabolic are usually exergonic. And what can we say about those, right? It means that anabolic is non-spontaneous. And catabolic is spontaneous. Oh my god, I don't know how to spell. So what does that mean then? It means, if you get this as a question, it means that delta G is negative for catabolic processes and delta G is positive for anabolic processes. So this is like kind of like your cheat sheet, right? It's really important that you know these terms. So endergonic means that energy was brought into the system. A chemical reaction required energy for it to proceed. Well, that's the case for both endergonic and exergonic. What I'm trying to say is that energy was put in to make a product that was not. If you'll excuse me for one moment. Okay, I'm back. Sorry. So, sorry, where was I? So, energonic means that we're gonna end up with less. Okay, how do I explain this? Okay, energonic means that we're gonna end up with more free energy than what we started with, right? So, what does that mean? That means that the energy in the system is going to be increased. It's going to require more energy than what we started with. Exergonic is when energy is released from the system. So we're going to have less energy than what we started with. So we can go ahead and look back at those energy diagrams. So I ask this now. Which oh, okay, well it actually just gives you the answer. So look at this again, right? Here we have exergonic versus endergonic, right? Where endergonic is, of course, delta G is a positive, and exergonic is delta G is negative, right? So these are kind of reversed. Um, but look at these graphs, right? So here on this side, we're ending up with less energy than what we started with. Here on this side, we're ending up with more. So why is that important, right? When we end up with more energy, then it's endergonic, we're building it up, and it's going to be, and if we're talking about biological processes, it's going to be anabolic, the inverse for exergonic. If we end up with less, then it's going to be exergonic, and we're breaking something down, meaning that this process is going to be catabolic. So these are like the primary differences in all of these processes. So bringing it full circle, sorry, bringing it full circle, where does that leave us with number 8? The citric acid cycle participated in anabolic processes. Well, what are we doing in the citric acid cycle? We are taking acetyl-CoA, right? We're taking acetyl-CoA that we made in pyruvate oxidation, and we are breaking that down into where we are oxidizing acetyl-CoA in multiple steps to make NADH, FADH2, and a little bit of ATP. That's what's happening in the citric acid cycle. So when we're talking about something that's being oxidized, more likely than not, it means that something's being broken down. That's not really a rule, so I would take that with a grain of salt. However, in the citric acid cycle, the citric acid cycle is part of cell respiration, correct? And cell respiration is a one long catabolic process. So why would we start building something up if we're already in the process of breaking something down, right? So citric acid cycle would not be a catabolic process. Sorry, it would not be an anabolic process. It would be a catabolic process. We are breaking something down so we can make ATP. We're breaking down glucose to eventually give us the energy in the form of ATP. So this one is false. Number 8. So number 9, pyruvate oxidation and the citric acid cycle complete the breakdown of glucose in the mitochondrial matrix. So pyruvate oxidation and the citric acid cycle. One sec. I just want to make sure this is correct. Okay, so yeah. Sorry. So let's make another quick diagram. So we have our 4 processes, right? We have glycolysis, glycolysis. We have pyruvate oxidation. We have citric acid cycle. And then we have the EDC. So, where do these occur? Glycolysis occurs in the cytosol. Pyruvate oxidation occurs in the mitochondrial matrix. The citric acid cycle also works in the mitochondrial matrix, and guess what? The ETC also does in the mitochondrial matrix. However, it's mitochondrial matrix slash intermembrane space. Because as you saw earlier, we need to transport the protons across the intermembrane space, and yeah, so you saw that earlier. But for this question, what we're focusing on is pyruvate oxidation and the citric acid cycle taking place in the mitochondrial matrix. And I'm just okay. I'm gonna take this question at face value. I'm going to okay. I'm just gonna take it at face value, right? So we're breaking down glucose. We're completing the breakdown of glucose, right? Okay, so in the ETC, right, or if you remember in the ETC, we're utilizing everything that we made in glycolysis, pyruvate oxidation, and citric acid cycle. We're not making anything new. in the ETC. We're just using all the stuff that we made to make ATP. So I would say the breakdown of glucose ends in the citric acid cycle. So we just went over all the locations of these processes. So I would say the answer is true. Sorry. Oh my gosh, it's 35 minutes in and we're not even done with question 10. So sorry, I'm just kind of frustrated with myself for taking forever. Anyway, so number 10 is asking protons can only cross the inner membrane space through the mitochondrial matrix through proteins complexes called ATP synthase. So let's look at ATP synthase. It's kind of funny. Some people call ATP synthase the ATP bong. That's because it's kind of what it looks like. So you could remember it like that if you really so want to. But so let's look at our ATP bong, right? Let's look at that. That's a little too big. Okay, that's better. So what's happening here, right? So if you remember, look at the charge in these protons. It's positive, right? Or if it were negative, doesn't matter. These particles are charged. And look at this membrane. It's the same membrane. It's the same stuff that the cell membranes are made out of. All these membranes have these lipid bilayer in common, right? That's what they all have in common. So these particles are not going to be able to cross, right? They're not going to be able to cross. So when we're saying protons can only cross protons can only cross the inner membrane space into the mitochondrial matrix through a protein complex called ATP synthase. Well, that's exactly what's happening, right? Look at what's happening here. The entire point of the ETC is that we push these protons across the membrane space. We push it across so protons can eventually go through the ATP synthase, creating a sort of like it basically just powers a generator, and this generator is making ATP. It's turning ADP plus a phosphate into ATP. This is a very specific process, and it's kind of a miracle that it's even able to occur. Anyway, this is the only way that protons are able to cross the inner membrane space. It is through this complex. Otherwise, they're not able to go back in. They're not able to go back in. They're only able to go in through this protein. So this is true. So that was the true or false questions. Like I said, I'm pretty confident on most of them, but they could be wrong. I mean, I told you my process. I told you why I think those answers are the way that they are, but they could be wrong. I could have came to an incorrect conclusion in logic, in which I apologize. But anyway, we're gonna move on from the true or false. So. Let's move on to questions 11, 12, and 13. So if you'll excuse me. So it's also important to note, right? It's also important to note that the multiple choice is worth a lot more than the true or false. So even if you do miss a couple of true or false, it's not that big of a deal. So which term most precisely describes the cellular process of breaking down large molecules into smaller ones? So we kind of already went over this, right? The difference between anabolism and catabolism, right? So it wouldn't be synthesis, it wouldn't be dehydration, right? The synthesis and dehydration, what do these have in common? Building something up, of course. So breaking down, we're not going to do either of these. Metabolism, that would be a good guess, but that's also incorrect because that encompasses both catabolism and anabolism, in which we're just talking about breaking down large molecules. So anabolism would not be breaking down; it would be building up, of course. So that would be incorrect, leaving only catabolism as the correct answer. Breaking down large molecules into smaller ones. So if you think about If you just excuse me for one moment, I need to take a drink of water. Sorry. So, just think about the difference between the cellular. Just think about the difference between cellular respiration and photosynthesis, right? Just think about those. Just think about the general chemical formula for those processes. Just one moment. I need to find. I need to find like a good image for this. Sorry, I'm gonna do this and I hope for the best. 1 second. Okay. Okay, that's good enough. So look at this. This is the decomposition of glucose into carbon dioxide and water. Of course, we're missing delta H, aka heat, aka energy, on this side, right? So we're releasing energy in this process, right? Or actually, better yet, plus ATP, right? So look at this. We're taking something big, glucose, and we're breaking it down into something small, right? And then we take the inverse of this. We take the inverse of this. Then what happens? We take the inverse of this. Like, look at this. We're taking something small and we're making it into something big. So this would be cellular respiration, and this would be photosynthesis. So if you just think about those differences, right? In photosynthesis, plants are building themselves up. They're making sugars. They're building up sugars through sunlight to make something big out of carbon dioxide and out of water. In cellular respiration, we're taking something big. We're taking a sugar and we're breaking it down into something small, carbon dioxide and water, something that we don't need, right? So that would be the difference between catabolism and anabolism once again. So moving on, number 12. Which of the following descriptions would be an example of potential energy? A. The chemical bonds in a molecule of sucrose. The movement of a bicycle coasting down a hill, a spark emitted from the explosion of a firework, or the flood water rushing through a breach in a dam. So I'm just going to say this. The answer is, of course, A. So what do B through D have in common, right? Look at the language. Floodwater rushing through a breach in a dam. A spark emitted by the explosion of a firework. The movement of a bicycle coasting down a hill. So what do these all have in common? Energy, the process. Sorry. Look at the language. So movement, explosion, rushing through. This implies that something is in movement, something is happening. So that means the energy has to be kinetic. It has to be in the process of releasing an energy, of taking potential energy and turning that into kinetic, right? So when we're talking about A, however, chemical bonds in a molecule of sucrose. So remember, you could burn sugar, right? When you burn sugar, you caramelize it or whatever, but then it eventually turns like black, and then it's like inedible, right? I mean, when you're literally burning sugar, you're releasing energy. Sugar is being burnt. There's a combustion reaction going on there. So so sucrose has these high energy bonds that are able to be broken down into energy. So that would be a perfect example of potential energy. It has the capability to be broken down. Eventually it will be broken down. It has the bonds, it has everything that's able to be broken down. So it would be a perfect example of potential energy. Specifically, this would be chemical potential energy. So if we have the bicycle coasting down a hill, when the bicycle was on top of the hill, that would be gravitational potential energy. A spark emitted from a from a firework, that's well, once again that would be chemical potential energy, and then flow rushing through water in a dam. I'm not too sure. So anyway, moving on to number 13. So what is the name of the barrier which reactants must overcome for a chemical reaction to occur? That of course is activation energy. So look at these. So look at these terms, right? It wouldn't be heat because heat is something that's emitted from the reaction. It wouldn't be. Heat would not be. Yeah, no, it's not heat. Entropy. It wouldn't be entropy either because what is entropy? Entropy is a randomness of the system, right? So that's not something that reactants need to overcome. It's something that it's just an intrinsic property of the particles in the reaction. So entropy is not correct. Enthalpy, that would be a good guess, but enthalpy is just heat, right? Enthalpy just means heat for the most part. I mean, I anyway. So enthalpy just means heat in most cases. So enthalpy would be a result of the reaction. It would not be a barrier for something for it would not be a barrier for the reactions to overcome. It would just be a result. Once kind of like entropy, it would kind of be like an intrinsic property of the reaction. So if we're increasing or decreasing entropy, we're increasing or decreasing enthalpy, it's a result of the reaction. It is an intrinsic property. It's not something that must be overcome. And free energy, much like enthalpy and entropy, it's something that is a result. It is a result. It is not something that you have to overcome. It is an intrinsic property. So all of these are not helpful to the question anyway. They're not helpful to the question. The question is asking what is the barrier. So even just looking at the language, what's the barrier that reactants must overcome? Well, well, for something to be activated, it needs to cross a barrier, right? So the best answer would be activation energy. And of course, activation energy is, so if you look at, so I'm just going to draw it crudely, right? Right? So this is a reaction. Yeah, so anyway, so the space, so if we kind of cross the line here, so this would of course would be an exergonic reaction because we're ending up with less free energy than what we started with. So look at this, right? So this is our activation energy. This is something that we have to cross. This is a line that we have to cross. And over here we have like I don't know, delta negative delta G, which would mean positive delta S, so it would mean positive delta H. So all of these, look at this, all these are results of the reaction. There's not something that we have to overcome, like activation energy. So anyway, that was 11 through 13. Let's move on. I'm going to speed this up a little bit. Okay, so let's see. Okay. There we go. Perfect. So let's look at this. Right, the active site of an enzyme is a region that A binds a substrate for the enzyme, B is blocked by presence of regulation by the presence of coenzyme or cofactor, C binds allosteric regulators of the enzyme, or D binds non-competitive inhibitors of the enzyme. So for this, we need to understand the anatomy of an enzyme. So sorry, my cat is being a bit of a nuisance, so I have to take him off my desk. He's a little cutie. I love him, but he could be really kind of pain in the ass sometimes. Anyway, so let's look at the anatomy of an enzyme. I need to have a good example of one with an allosteric site. Okay, this is I'm gonna use a couple of different examples. So I'll use this one, and then I'll use this one. So I'll make this one a little smaller. So look at these. Look at what's happening here, right? So this is of course our enzyme, right? And so we have a couple of different things about the enzyme, right? So here we have an allosteric site, and here we have an active site. So the active site is where the substrate is actually being turned into a product, where we're taking a reactant and we're turning it into a product, where we're actually doing chemistry on something. That is where the active site occur. That's where the active site happens. I mean, just look at the language. Active site. I mean, something needs to be active. Something needs to be activated. Something needs to be made alive, even. So that's what's happening at the active site, right? And then look at the allosteric site. I mean, the allosteric site. I mean, just the wording is not as helpful as active site, but allosteric site is where other stuff can happen, right? That's not really helpful. So either at the allosteric site we could have an inhibitor, and this inhibitor can do what's implied, and it can block the binding of a substrate into the enzyme, right? That's what an inhibitor can do. Either it could, and then on the other side we have an activator, still at the allosteric site, right? The activator changes the shape of the enzyme so that the substrate can now bind. And so over here we have the inhibitor, which changes the shape of the enzyme so it can no longer bind. So that's kind of the difference, right? So we have the allosteric site, we have the active site, all that sort of stuff, and then we also have. So that's also what's kind of happening here. So this image up here is showing the difference between non-competitive and competitive inhibition. So competitive inhibition. So when we have something that is similar shape and property of the enzyme, property of the substrate, that's when we have competitive. So we have something that's literally blocking. We have something that's literally blocking the entry of the substrate into the active site, right? It's blocking it. It can't bind, right? So the substrate just gets blocked off. It goes somewhere else. So that's competitive inhibition. And then over here we have non-competitive inhibition. And this is what we're talking about, the inhibitor at the allosteric site. So much like here, where we have an allosteric site in which an inhibitor can bind, this is the allosteric site in which an inhibitor can bind. And then the inhibitor changes the shape of the enzyme, and the substrate goes on and goes somewhere else. So number 14 is asking, the active site of an enzyme is a region that D binds competitive inhibitors of the enzyme. That is incorrect, right? Because we just went over what that is. Binds allosteric regulators of the enzyme. That is also incorrect because that would happen at the allosteric site. B is blocked by the presence of coenzyme or cofactor. We'll get back to that one. Or A, binds substrates for the enzyme. So the answer is going to be A, right? Because we just went over that. So let's look at the cofactor real quick. So we just kind of went over the types of regulation, right? So here we have another one, right? So here we have a cofactor, right? So this is a cofactor. A cofactor actually goes on and binds to an active protein. So there's a bit of a typo here, right? These are your substrates, right? So now once the cofactor is bound, it actually goes on and becomes activated. So this would be an active protein, right? So without the cofactor, attached protein is not active. Cofactor binds, activates the protein. So that's what a cofactor does. So if you think of co means with, right? So when you're with something, when you're working together with something, that means you're gonna help it work, right? So cofactor helps it helps activate an enzyme. So active site would have to bind the substrate of the enzyme. That's the only logical answer. So anyway, let's look at look at this. We've gone over the free energy diagrams, haven't we? So let's go look at what's going on here. So 15 is asking which of the following best describes the reaction that's occurring? A plus B gets turned into C plus D, and this is a reversible. This is a reversible, which we don't really it doesn't really matter. So what's going on here? So look here. Free energy on the y-axis, progression of the direction on the x. So we're starting with a higher delta G. So free energy is delta G, right? And then we're starting with a lower delta G. So when we start with a lower, right? Sorry, when we start with a higher and we go to low, that means something is going to be exergonic. We're going to have less energy in the system because the energy is going to be released from the system, right? So through this, right, through this process, that would have to be exergonic. So exergonic, when something's exergonic, that means it is negative delta G. Refer to the diagram of anabolic versus catabolic I drew earlier, right? Of course, we know that exergonic means negative delta G, negative free energy, so the answer would be D. Exergonic, delta G is less than 0. So, sorry, I would. This is the time I would normally wake up at 8 o'clock. Anyway, which number 16 is asking which labeled area represents the overall delta G for the reaction. So, let's look at that, right? Overall delta G. So look at where we started, right? We started here and we ended here. So what is the line that best represents that? That would be D, right? Because we're looking at the net energy. So the delta G would be the net free energy that was either released or absorbed, right? So look at where we're starting. Once again, look at where we're starting and look at where we're ending, and that would be D. That would be represented by D. We started here and we ended here. So that would be the overall delta G. So why wouldn't it be E? Which is a good question, right? E would be the total energy, I think. I'm honestly not 100% sure. E would be like the total energy used in the system. So here we have the very, very top and the very, very bottom. So this would be like the total energy. But of course, what is the net energy? Start positive, go negative. That would be D. That would be the overall delta G. Which in fact, I'm gonna put a star next to this one. I'm honestly not 100% sure if it'll be D or E. Anyway, sorry, I'm just kind of working through the process. um, anyway, so number 17. Which of the following which of the following represents the activation energy if no enzyme is available? So remember, what does an enzyme do? It lowers the activation energy, right? That's what an enzyme does. We went over that earlier, right? It lowers the activation energy. So if we don't have an enzyme, then the activation energy is going to be higher. So, so B would be our enzyme catalyzed reaction, and then C, because it's larger, right? We're going from here to here, right? That's what's going on, right? Sorry, this is really kind of messy. So this would be our enzyme catalyzed, and this would be our non-enzyme catalyzed because one is larger than the other. You require more energy. If something requires more energy, then it is not enzyme catalyzed. So the answer will be C. So which line represents the progression of a reaction when it is catalyzed by an enzyme? So that would be, of course, 2. It would be B, 2. So once again, I mean, just look at what's going on. I mean, we answered 17, right? So if we answer 17, then 18 is going to be opposite, right? So yeah, Um, sorry. So yeah, we answered that. Of course, this is the B is our non cat B is our catalyzed reaction. So where is B? Right? B is two. B represents two. Right? So that would be our catalyzed reaction. So 18 would be two, and then it's the opposite for 17, which we already went over. So anyway, um, which of the following best describes a reaction A plus B gives you C plus D? This reaction releases energy. So once again, it's kind of one of those things that you just like if you refer back to like the diagram I drew, right? If you refer back to like that sort of T chart, you'll see that okay, so even just looking at the reaction, right? We ended up with less energy than what we started with. So where does that energy go? That energy has to go somewhere, right? So therefore, it has to go somewhere. It needs to release the energy. The answer would be A. Endergonic would consume energy. Now, I'm going to say this. This question is going to be very, very important. These questions are very, very important. Please study these questions. You will almost certainly see them on your exam. So, yeah. I'm just going to look something up real quick. If you'll excuse me for one moment, my apologies. Okay, anyway, sorry. I'm really unsure what E means. So I would ask Dvorka about what the difference between E and D is. Um, so I want to ask her, as a matter of fact. So we're gonna go back to that later. Sorry about that. Sorry about the little delay. I just had to make sure that I wasn't feeding you misinformation. I really hope I still wasn't feeding you misinformation because I couldn't find anything on the internet. On quickly anyway, I couldn't find anything. So anyway, let's move on. So we're gonna go through 20 to 25. Let's see what we're doing on time. We're just past the hour mark a couple minutes ago, so let's finish this up quickly. Yes. So okay, so number 20 is asking during glycolysis, a glucose molecule will be split up into 2 3 carbon molecules. Okay, so I I mean I know the answer to this question, but I don't really like. Okay, okay. Well, no. Actually, look at this. Look at this. During glycolysis, so glycolysis, we can immediately. So look at our answers, right? Glycolysis, we don't make acetyl CoA. Glycolysis, we don't release CO2. We don't. Okay, NADH does not include carbon. ATP does not include carbon, leaving only pyruvate as the answer. So let's look at our let's look at what's going on during glycolysis. Let's look at that real quick. Okay, I'm gonna put up a couple. Okay, I'm gonna resize this. Hold on. Oh, perfect. Okay, so look what's going on here. So this is more for like biochemistry, but so like just look at all these steps that are occurring, right? We take like 10 steps, 10 enzymes to turn glucose into pyruvate, right? So this process is super important, but look at what's being made. ATP, NADH, and pyruvate, in which we're making two pyruvates. So that's another thing. That's another important note. So during glycolysis, glycolysis is split in half. Glycolysis, glucose cut. So glycolysis, we're turning glucose into two pyruvate. So glucose has how many carbon molecules? Sorry, carbon atoms? 6. How many does pyruvate have? 3. So we're literally splitting it in half. We're not releasing any CO2 in this reaction. We're not releasing any CO2 in this process. So the only logical answer would be pyruvate. I mean, even if you didn't know all of these, so we're making so glycolysis, just know the end products, right? Acetyl CoA is not made until pyruvate oxidation. ATP and CO2, sorry, ATP and NADH don't even include carbon. Well, they do, but not the kind that we're looking for. And then CO2 is not releasing this reaction either. If CO2 were, then glycolysis would not be split up into 3 carbon molecules, because carbon dioxide would be split up, would be elsewhere. So just using the question, you could already just kind of make an inference. You can kind of make a guess as to what's going on. So this might be a better diagram for the purposes of this class. I'm gonna resize this real quick. Let's do 40. That's too much. Let's do 60 actually. That's perfect. Okay, so just ignore all the stuff in the middle. We don't really care about this. Shoot, we don't really care about the stuff in the middle, right? What we care about is what we're starting with, a 6 carbon molecule, and then what we're ending with 2 3 carbon molecules, and ATP and NADH, which it's not here. I don't know where the NADH is. So we ended up with 2 pyruvates, right? 2 pyruvates from 1 glucose. It's just something I really want to emphasize. All right, moving on. What is the last product of glycolysis? So this question works in tandem with number 20, right? If you know number 20, then you know number 21. So what is the last product of glycolysis? Well, it wouldn't be glucose, obviously, because we're breaking down glucose. I mean, and look at these other answers. I mean, did we even go over phosphoglycerate? No. That's something if you're a biochemistry major, then eventually you'll take biochemistry. You'll know what PEP and you'll know what phosphoglycerate is. But the only logical answer would be pyruvate. We didn't even go over these. I mean, that really would be unfair if literally answers. Last part of glycolysis is pyruvate. That's the only one that we've actually focused on. So pyruvate oxidation reduces 1 NAD per molecule, produces ATP via substrate level phosphorylation per molecule, occurs in the cytosol. So this one's wrong, and I think this one's not wrong as well. Well, maybe not. Let's look at pyruvate oxidation. So remember, so glycolysis occurs in the cytosol, right? And then pyruvate oxidation and the citric acid cycle occurs in the cytosol. Sorry, in the mitochondrial matrix, right? So that's another thing that I want to emphasize is where the locations of these happen. So let's see. So pyruvate, so we turn pyruvate into acetyl CoA, but look at what we're also doing. We're reducing NAD into NAD plus into NADH. So the answer would be C. Sorry, I knew that. I had a feeling that was the answer. I had some second guesses. Anyway. So, if we look at what's going on here, right? So, I will say this. Reduction and oxidation need to occur simultaneously. Right? They need to occur at the same time. For something to be oxidized, something needs to be reduced. And for something to be reduced, something needs to be oxidized. So when we're talking about pyruvate oxidation, Well, something needs to be reduced then if pyruvate is being oxidized, and in this case, NAD will be reduced. So, and we're taking one pyruvate. For each one pyruvate, we're making one NAD. Or we're making one NADH from one NAD+. So, anyway, moving on. Which type of ATP production is done in the citric acid cycle? So we have our different types of phosphorylation, right? And we're going to go over that now. So we have oxidative phosphorylation, photophosphorylation, and substrate level phosphorylation. So what are these, right? Oxidative phosphorylation only occurs in the ETC, right? It only occurs in the ETC. Because remember what's going on in the oxidative phosphorylation. All those NADHs that we made throughout cellular respiration, all those NADHs are being oxidized. So we're releasing those protons, and then those protons power ATP synthase. So that's like kind of like the magic of it all, right? But for it to be powered, NADH first needs to be oxidized, right? So there isn't like a whole lot of change there. So basically NADH we weren't turning NADH into ATP. We're turning NADH into NAD+. So we now have a free proton, and that proton goes on to make ATP, right, through ATP synthase. Right? So that's oxidative phosphorylation. And then photophosphorylation, that is just photosynthesis, right? So photo means light. So I'll write that down. Photo means light. That's more Latin or Greek for you. It's probably, I think that's Greek. Anyway, photo means light. So what is the only process that we've learned about that requires light? Photosynthesis, right? So photophosphorylation, something needs to be phosphorylated. ATP needs to be phosphorylated through light. So that wouldn't be in the citric acid cycle. So citric acid cycle would be substrate level phosphorylation. So you think about the citric acid cycle, it's an entire cycle of like 8 enzymes, right? Those enzymes are constantly doing chemistry on products. It works as a cycle, of course. So let's look at the citric acid cycle. I'm gonna choose the most simplified one. So even then, we don't even really care about the ATP that's Jesus. We don't really care about the ATP that's produced during the citric acid cycle. We're really focusing on NADH and FADH too. This one doesn't even show ATP being produced, right? So, but look at this. All these enzymes are turning stuff into other stuff, right? We are phosphorylating via enzymes, and that is substrate level phosphorylation. When we're doing it via an enzyme, so not through a long process of electrons and chains and proteins. We're doing it, and not through light. We're doing it through substrates, through substrate level, aka through enzyme. It's a long way explanation. So let's move on. Anyway, so number 24, most CO2 from catabolism is released during C, the citric acid cycle. So, okay, sorry. So actually, and it's gone forever. Okay. So let's look at the citric acid cycle, right? So another thing I want to emphasize is you need to know what is released and what is put into the different processes, in which I can go over that later. So look at this diagram, right? So here we have oxaloacetate, right? Oxaloacetate is a 4-carbon structure. Acetyl-CoA is a 2-carbon structure. 4 plus 2, of course, equals 6. But to get oxaloacetate, we're going to break down citrate. We're going to break this down. We're going to release 2 carbon molecules in the form of CO2. And as you saw earlier, right? As you saw earlier, pyruvate oxidation also released carbon dioxide, but it only released 1, right? So even if you multiply it by 2, if we have 2 pyruvates, then 2 pyruvates into 2 acetyl-CoAs, then we have 2 CO2s. But then if you have 2 acetyl-CoAs and they have 2 per, that's 4 CO2 total. So there's a lot of CO2 that's being released, right? So CO2, that would be during the citric acid cycle. And then oxidative phosphorylation does not release CO2. ETC does not release CO2, and glycolysis, as we went over earlier, does not release CO2. So the answer would be C. 25. If you made a list of molecules that gain energy after the electron transfer chain is finished, which compound would go in the list? ATP, without a doubt. So if we're talking about the ETC, we're not even worried about glucose and pyruvate. Those are way far behind, right? Those are like, we don't even care about that stuff. That stuff is like at the very beginning, right? That is all in glycolysis, and we don't care about glycolysis right now. So, which molecule gains energy? NADH is releasing energy. That is the thing that's being oxidized. It is releasing energy by being oxidized. Same thing with FADH2. It is releasing energy by being oxidized because it's oxidative phosphorylation. And what are we making? We're making ATP. What is ATP? ATP is a high energy compound. So if we made a list of molecules that gain energy, the only logical answer is going to be ATP. So let's move on. Alright, so we're on the last 5. Okay, well, let's go over these 2 and let's go over the last 3. Because it's kind of split up in a kind of strange way. Anyway, so let's go over 26 and 27. Number 26 says, which of the processes is least economically efficient in terms of ATP produced per molecule of glucose? So let's see what's going on here. Lactic acid fermentation. Well, that's kind of the same thing as B, or anaerobic cell respiration. The answer is just B. All right, I will say this. The answer is B. So lactic acid fermentation. It could be B or C. Honestly, I think I'm gonna put a star next to this one as well because it could be either one. I'm not 100% sure. It's certainly not aerobic cell respiration. So remember, if we have 1 molecule of glucose, aerobic cell respiration will give us like 30 something ATP molecules, right? And Dvorkin just kind of went over this on Wednesday, right? When we're talking about anaerobic cell respiration, that it's super inefficient. We're just doing glycolysis during anaerobic cell respiration. We're just doing glycolysis. And remember how much ATP is produced during glycolysis. Literally 2 ATP. So that's like nothing compared to aerobic cell respiration. And like I said, lactic acid fermentation, that's just anaerobic cell respiration. They're like the same thing. Kind of. So lactic acid fermentation would be an example of anaerobic cell respiration. So I would say the answer is B because like I said, there's like barely any glucose that's being made. Barely any. Barely any ATP that's being made compared to aerobic. Anaerobic would be with a lack of oxygen. And when we're lacking oxygen, we're lacking that final electron acceptor in the ETC. When we're lacking that means like everything, we can't do anything. We can't do the citric acid cycle. We can't do pyruvate oxidation. All we have to do is we have to make as much pyruvate as possible for lactic acid fermentation, right? For anaerobic cell respiration. So we could, yeah. Anyway, I'm just rambling at this point. But the point I'm trying to make, barely any ATP is being made. Number 27. The energy of energy of electron transport serves to move protons to the outer mitochondrial compartment. How does this help a mitochondrion produce ATP? So we went over this a little bit with the ATP bond, right? We went over that. So protons. So D, the protons are transferred to oxygen in an energy releasing reaction. That is incorrect. The electrons are transferred to oxygen. C, the movement of protons sets up the electrochemical gradient that drives ATP synthesis in the mitochondria. That is definitely correct. Protons receive electrons. That doesn't even make any sense. Protons receive electrons. If that were the case, then this one, okay, just ignore this one. This answer sucks. This answer is like the most incorrect. And A, protons pick up electrons from the electron transport chain on their way. This one's also incorrect. So protons receive electrons from NADH. I mean, A and B are basically the same thing. They're basically saying the same thing. Protons receive electrons, they pick up electrons. That is not at all what's happening. That is not at all what's happening. So what's happening is the movement of protons sets up the electrochemical gradient. It's like a dam, right? It's like a dam. That's what's happening. Sets up electrochemical gradient that drives ATP synthesis in the mitochondria. It's that movement of the protons. It's how we're getting protons from one point to another. It's like water through a dam. It's powering a generator that's making ATP synthesis. That's making ATP. It's powering ATP synthesis. So, moving on. Number 28 through 30, and these are your photosynthesis questions. Now, photosynthesis is a very complex process that we don't really care about because we're not plants. So let's look at this. So you and I, just judging from what we learned in class, this is pretty much all that we need to know. There's 3 questions of photosynthesis. We went over like maybe 40-30 minute lecture, 40-minute slideshow about photosynthesis. There's not a lot about photosynthesis that we need to know. That's our secret. So let's look at photosynthesis. One thing we want to emphasize is the light that plants absorb, what's put in, what's put out, and once again, what's put in and put out. So one thing I want to emphasize about photosynthesis, the entire process of photosynthesis, you don't really need to know. You don't need to know that oh well, excuse me. Okay, well a photon gets absorbed into like a photosystem, and the photosystem makes ATP, and the ATP powers you don't need to know any of that. What you do need to know, however, is the high energy light that's being produced. So, what 2 colors of the list of number 28 is asking what 2 colors of the list drive most of the photosynthesis. So, think about what color a plant is. Green, right? So that means that plants are reflecting green light. They are absorbing all that good and powerful red and violet light, right? They're absorbing all that high energy light. So anything with green, so A, B, D, all incorrect because we're seeing green. We see a plant, we are seeing green. The chloroplasts are reflecting out green into our eyes. So then we look at red and yellow, right? So if we look at the diagram itself, right, we can see green over here and we can see yellow over here. Well, look at what's being absorbed. So we look on the y-axis, relative effectiveness in photosynthesis. I mean, that's literally like this graph literally gives you the answer. So we look at we look at relative effectiveness. Well, green and yellow are on the very bottom, and then blue and red are at the very top. They have the most effectiveness in terms of light absorption. So the answer would be C, red and blue. Red and yellow would also be incorrect. So anyway, the Calvin cycle requires all of the following except. So remember we talked about Rubisco. We talked about everything, right? So let's look at the Calvin cycle, right? So the Calvin cycle was like quite there. Shoot. Okay. Reconnection successful. Okay, we're I think we're back online. Okay. I don't know what happened there. Sorry about that. I'm gonna have to check it in stream if that was poorly affected. The stream is fine. Sorry, the stream is fine. Let's go back into dissing photosynthesis. Yes. So let's see. Okay, this is perfect. So this is their Calvin cycle, right? So we talked about how important Rubisco is, right? So Rubisco is definitely something we need. CO2 is definitely very important. CO2 is what makes up the sugars. CO2 very important. Rubisco very important. NADPH also important. So we need all of these, right? So remember, what do plants release? What do plants not need? Oxygen, right? Plants just put out the oxygen into the air, right? We breathe the oxygen that they make. Look at what's not here. G3P plus ATP used to make RUBP, and then RUBP, and then we need RUBP gets broken down via um, via Rubisco. So Rubisco is one of the most important enzymes that we need to know about. CO2 is very important in the Calvin cycle because that's how we build the sugars. NADPH powers the Calvin cycle. It's what puts in the energy, and ATP also puts in the energy, leaving only oxygen as our most logical answer. So, hey, oxygen. So number 30, the splitting of water in photosynthesis provides CO2 and electrons, glucose and electrons, hydrogen ions and energy, O2 and electrons, and O2, H2O, and ATP. So, if I had to guess, it would be C. So you and I, we probably wouldn't study this if we're being honest. So let's just think about what's going on here. So if we're splitting water, right? If we're splitting water, then most likely we're going to make O2 and we're going to make electrons. So obviously we wouldn't make. Okay, look at some of these answers. Splitting of water, why would that produce CO2? That doesn't make sense. And it provides glucose, that also wouldn't make sense because the G3P provides glucose, right? The splitting of water does not do that. So that leaves only hydrogen ions, energy, O2, and electrons. It's most likely O2 and electrons. So let's look at this. So now we're kind of talking about a little bit about the photosystems and okay, let's see. So yeah, look at how similar this process. Okay, that's kind of crappy. Okay, let's resize. That's good enough. Okay, so let's look at what's going on here, right? So we're talking about the splitting of water that occurs during photosystem 2. Um, like I said, it's really not important that you study this. I just don't think that it is. I mean, look how many questions there are. There's three. There's three. I mean, I just want to emphasize that you don't study something that you don't need to. So the splitting of water obviously would not produce electrons or CO2. It obviously wouldn't. Sorry, it would not obviously not produce CO2 or glucose. That's just obvious, right? But it would produce electrons, right? And it would produce O2, right? So why would the splitting of water? Once again, look at this. Look at these answers. Why would the splitting of water produce water? That doesn't make any sense. So E would also be incorrect. So just if you're stuck on a question, if you're confused about a question, just use common sense, or it's not even really common sense. Just use logic. That's better because this isn't really common. Some of these answers are common sense. Like why would splitting of water produce water? That doesn't make any sense. But you just have to use logic as well. Why would the splitting of water produce carbon molecules, right? So the only logical answers would be hydrogen ions or energy, right? In which it would produce hydrogen ions, that is true, but it also wouldn't produce energy. It would produce an electron, right? And the electron goes through the photosystem, and then it's powered through light, but it doesn't. It in itself does not produce energy. However, it does produce oxygen, which, if you remember, oxygen is one of so oxygen photosynthesis is the kind of opposite of cell respiration. So cell respiration, we're putting in oxygen and we're getting out water. Photosynthesis, we're putting in water and we're getting out oxygen. So oxygen would be a byproduct. So splitting of water, that would that would probably, like, logically, that would probably produce oxygen, right? And it does, right? So anyway, that is your exam 3 review. there is some other stuff that I would like to go over. Something I just want to emphasize is that oxygen is your final electron acceptor in the electron transport chain, right? That's your final. That's the only time in which we're using oxygen in that process. So just think about everything that's going in, everything that's going out in all these processes. Look at all the diagrams that you were given throughout class. Think about what goes in glycolysis, what comes out. So what goes in, glucose, NAD plus, ADP. What comes out, ATP, pyruvate, two pyruvate molecules, and then NADH. What goes in, pyruvate oxidation? Well, obviously pyruvate. Then coenzyme A has to come in, and then NAD plus has to come in, and then because we're oxidizing pyruvate, we're gonna turn all that into NADH and acetyl CoA, as well as one CO2 molecule. And then think about the Krebs cycle or the citric acid cycle. We're putting in acetyl CoA, right? And we're putting in acetyl CoA, some ADP, some GDP, a lot of NAD plus, some FAD, and then out of that we're getting some ATP, a lot of NADH, um, some and then some FADH too, and then we're also getting out like the coenzyme A, but the coenzyme A gets reused. So it's also important to note that coenzyme A gets reused because it is an enzyme after all. Anyway, and then what's happening in the citric and what's happening in the ETC? Well, we're using everything that we use up to this point, right? So we're putting in all the NADH, we're putting in the FADH too, we're putting in all that stuff, and then we're getting out NAD plus and FAD, right? In order, and then we're doing all of that, right, to to turn ADP into ATP. So it's really important that you know these processes, right? It's really important that you know these processes. So I've come up with sort of like four different levels in which you have to know this stuff, right? So level one is just you have to know the process of what's going on of cell respiration. So cell respiration, I think of like in four different like levels, four different tiers of what you have to know. Level one. So currently we're at level two. Level one is just knowing the process. So knowing like what's happening. Level two is knowing what goes in, what comes out. Level three is knowing all the enzymes. Sorry, wait, no. Level three is knowing every single substrate, like every single intermediate, and then level four is knowing every single intermediate and every single enzyme. Currently, we are at level two, so do not worry yourselves. Study your diagrams, please. But in any case, I bid you all farewell, and I hope you have a good exam. And otherwise, after that, I hope you have a good weekend. So take care.